Sometimes in order to approximate a curve, so let's say we have a curve y equals f of x, around a specific point, so for example, a comma f of a, okay, we can use the tangent line to the curve. So this is an example of how we can use the derivative to approximate a more complicated curve in a particular area. So we're really interested in just what's happening in the area right around a comma f of a. So let's have a look at what that means. So if we draw a graph of f of x, and we have a lovely, beautiful f of x here, let's say we have a point A. And if we draw the line tangent to f of x at A, we can see, so this is at f of A. So if we look at this tangent line right here, what we can see is that when we're really close, when we're in this little neighborhood around A, the closer and closer we get, the better and better approximation for the whole curve that tangent line is. So what we do is we take this and we extend it. And we're going to find a formula for how to write this tangent line, and we can call it a linearization of f of x around f of a. And this is the same as the tangent line that we would be calculating. This is the line tangent to f of x at a. So, okay, so we will define, so let L of x be the linearization of y equals f of x around, okay, a point x. Okay, so we're going to derive f of x. Okay, so we want, for L of x, we want f of a to be equal to L of a. We want the linearization to have the same point, to actually pass through that point. And we want f prime of a to equal L prime of a. So we want the derivative of the point to be the slope of the line. Okay, which means we are finding the line that is tangent. Okay, so let's let L of x equal mx plus b. Okay, L prime of x is going to equal m. So L prime, because we want L prime at a to be f prime at a, so L prime at a is equal to our m, which is equal to f prime of a. So that's the slope of our line. Okay, so we want the linearization at a to be the same as f at a. So we want it's going to be equal to m times a plus b. We want now this to also be equal to f of a. So we want the function to be the same. So this means we know, but earlier we said we want f prime of a to be our slope. So f prime of a times a plus b is equal to f of a. Okay, so if we want to calculate b, b is equal to f of a minus f prime of a times a. So we can actually get a formula here, linearization, for the tangent line of f at x. So L of x is equal to m times x plus b, which is equal to f prime at a. Okay, so we're looking at f of a. So now we're going to see what L of a is equal to. F prime of a times x plus f of a minus f prime of a times a. Okay, so this was B and this was M. We're just replacing those. Okay, so that means our linearization at A, if we combine like terms that have an f prime of A in it, is this is equal to f at A, so our original point, plus f prime of A times x minus A. So this is a direct equation for finding the tangent line of a point around x equals A. So that is lovely because the tangent line approximation is the one we're looking for. Same slope, same point. And it's nice to be able to find it directly. So if we can do a linear equation, so let's say we have a curved function. So a line is at best kind of a mediocre approximation for a curved function. What if we could approximate around that curved function with a curve? So we also actually have a quadraticization. So we can write it as a quadratic equation. And in your second semester of university calculus, you will be looking at how you can actually get an nth degree polynomial that will approximate your function to better and better degrees and further out from the point. So the higher degree of the polynomial, the better approximation it's going to make of your function. So the quadraticization of A is f of A plus f prime of A times x minus A plus f double prime of A over 2 factorial times x minus A squared. We could also have a cubic. So this would be, and these are called Taylor polynomials. And you will be investigating those, as I said, in Calc 2, I believe. So this is f of A plus f prime of A, x minus A, plus f double prime of A over 2 factorial x minus A squared, plus f triple prime of A over 3 factorial times x minus A cubed. Okay, and we can keep going with quadratic, etc. So what's the usefulness of this? Well, a lot of these approximations were developed when calculators, particularly of the scientific variety, were not widely available. So this calculus made it easier to do certain calculations that were not at all easy to do without. So let's say, example 1, find root 4.05 using a linear and quadratic approximation of the function f of x equals radical x plus 3 around x equals 1. Okay, so we're going to be looking at the point around the point where x equals 1. So if we're trying to do the linearization in that region, we're going to let our a equal 1. So f of x, which is approximately equal to L of x. So f of x is going to be approximately equal to L of x. L of x, L at A, is equal to f of A plus f prime of A x times x minus A. So our point A is going to be 1. Okay, so f prime of x, using the chain rule, we have 1/2 times x plus 3 to the minus 1/2. Inner derivative is just 1, so it's times 1. Okay, so 4.05 equals 1.05 plus 3. We're going to use the linearization around the point 1. So that means this 1.05 is going to be our x, and our a is going to be 1, because we're going to use the tangent line to the graph x at x plus a, because that makes our computations easier. Okay? So our linearization at x is going to be equal to, at a, sorry, I wasn't super precise with that. That should be linearization of x at a, okay, is going to be equal to f of a plus f prime of a times x minus a. So we are using a linear approximation around a. So f of a is the square root of 1 plus 3, because a is 3, plus f prime of a, which is 1/2 times 1 plus 3 to the negative 1/2. And then we're going to be multiplying by the difference between x and a. So 1.05 is just 0.5 more, 0.05 more than x. So here we get, this is equal to 2 plus 1/2 times 2 to the negative 1/2, which gives us 1/4 times 0.05. And a quarter of 0.05 is 0.125. Think of it as 50, so it's 12.5. So this is 2.0125, and that's something that someone could have done in their head. And so if we were to check that using a calculator, the square root of 4.05 is actually equal to 2.012461118. So it's actually accurate to 4 decimal places, which is pretty impressive. Okay, let's try a quadratic approximation and see if that is any more accurate. So again, we have f of x equals radical x plus 3. We have f prime of x is 1/2 x plus 3 to the minus 1/2. And f double prime of x equals, let's write quadratic just so we know what we're doing here. And f double prime of x is negative 1/4 x plus 3 to the negative 3/2. And we have, from the last time, we have a equals 1, x minus a equals 0.05. Okay, so f of x will be, in that region, will be approximately equal to q of x, which is f of a plus f prime at a times x minus a plus f double prime at a over 2 factorial, sorry, that made that kind of a question mark, eh? 2 factorial times x minus a squared. Okay, so now we can plug that in. This was 2. This was 0.0125 from the last time, plus f double prime of a. So we're going to plug in 1 to f double prime. So 4 to the negative 3/2. So 4 to the 1/2 is 2. 2 to the negative 3 is 1/8. So that is negative 1/4 times 1/8 x minus a squared. And we have our times 1/2 from our 2 factorial. 2 factorial is just 2 times 1, which is 2. 1/2 and 0.05 squared. So this is equal to 2 plus 0.0125 plus 1 over 25,600. And that ends up being equal to 2.0124661, and you can see that is even more accurate. That's actually accurate now to actually 6 decimal places, which again, pretty impressive. Okay, so let's do another example, this time with trigonometry. So we are going to find the linear, so it's really clear we're stopping there, find the linear approximation of y equals sine x, and use it to approximate sine 59 degrees. Okay, so let a equal 60 degrees equal pi over 3. Okay, y at pi over 3 equals sine pi over 3 equals root 3 over 2. Sine of pi over 3 is the long one, cosine is the short one. Y prime equals cosine x. So y prime at pi over 3 is going to be the short one, so cosine pi over 3 is 1/2. Okay. So for x equal 59 degrees, 59 pi over 180 is x, and 60 pi over 180 is a. So sine x is approximately equal to its linearization, right around the point, which is f of a plus f prime of a, and we're going to do it around, our a is going to be 60, and our x is going to be 59. Okay, so the x is always what we're trying to approximate. Prime of x minus a, so this is root 3 over 2 plus 1/2 times x minus a. So if we look at x is 59 pi over 180 minus 60 pi over 180. Okay, which is root 3 over 2 plus 1/2 times negative pi over 180, which is root 3 over 2 minus pi over 360, which is 0.857298. And if we throw that on a calculator, sine 59 degrees is 0.857167. So it is accurate to almost to about 3 decimal places. So again, pretty impressive for just a linearization. Notice though that this linearization technique is really effective. We're looking at the difference between sine 59 and sine 60. It would not be as accurate if we were trying to find, say, sine of 29 degrees. We'd want to use a different angle that we knew in order to be able to do that kind of approximation.